Hi, hello everyone. My name is Yongxi and my partner is Shurui. Today we are gonna present our final project for EE201C. So for this project, the problem that we are gonna solve is to reduce the overall spice run for estimating SRAM failure probability, hence to increase the efficiency and greatly reduce the overall running time for the algorithm compared to standard Monte Carlo algorithm. So the approach that we choose is to use high-dimensional importance sampling. As you can see here, the overall algorithm consists of several steps. First, we need to initial sampling with MC. Second, we need to calculate the conditional probability. And third, we need to use MATLAB to perform the failure probability estimation. The overall algorithm can be seen also in this in Figure 1. Since this is a presentation, I won't go too much details about how we implement this algorithm. You can find further information in our project report. So let's jump directly to the simulation and result. For simulation, we decide to simulate it for different cases. As you can see, for the proposed method, we first start the number of input samples at 1000 and then increase the number of samples 1000 by 1000 a time. And finally, when it reaches to 14,000, we stop. However, we can still play around with the t-value. We chose three cases for the t-value. First, we chose it to be 99%. Second, we chose it to be 99.25%. And third, we chose it to be 99.5%. And then we also have the reference simulation, which is the standard Monte Carlo method. Here's the result. The first figure is the failure probability versus number of samples. As you can see, the failure probability is approximately around 10 to the negative of 4 for all these four types of different cases of simulation. But you can see Monte Carlo method requires the input number of samples a lot more than the proposed algorithm. Let's look at the figure of merit versus number of samples. This figure directly tells us which one is the best case. So for the proposed algorithm, when t is equal to 99%, which is the blue curve, when the number of samples is approximately equal to 10,000, this algorithm converges. However, for the other two cases with the proposed algorithm that t is slightly greater than 99%, it looks like it needs more samples to converge. And for Monte Carlo method, it needs 2.3 times 10 to the 6 number of samples to converge. So the conclusion is that with the proposed algorithm, we only need let's start with the t. So as we can see, if the value of t is too big, which means it's very close to the 1 to 1, the algorithm is not that easy to convert. The reason can be seen as if the t is very close to tc, where tc is the failure region as proposed in the paper, the indicator I function might not be successful as many as when t is equal to 99%. So since we have a less number of success samples, then this algorithm might need more input samples to converge. Second, as we can see, the proposed method greatly reduced the overall hit-space run by reduced the sample from 2.3 million to approximately around 10,000. The percentage, the decreased percentage is around 230%, which is a huge number. So overall, this algorithm greatly reduced the overall simulation running time and increase the simulation efficiency by reducing the number of input samples. Thank you very much.